Hi, welcome back. So, in the previous lecture, we focused on matrices, matrix addition, matrix multiplication, and how to invert matrices. We focused our attention on how to invert a 2 by 2 matrix, but you can invert matrices of any size. In fact, in practice, matrices can be very, very large. They could have millions of entries. But for the purpose of encryption, we don't need very large matrices. In fact, 2 by 2 matrices do well enough. They do the job well enough. Okay. So behind me, I have a sentence in plain English. The ice cream was awesome. Now, previously I would take numbers which I called the key, and I would use these numbers to manipulate the position of our characters. So I'd either multiply or add the key to the position of my letter to get a encrypted position, right? So if I had, say, 4, which is the fourth letter of the English alphabet is D, and so if my key was 5, I could multiply 4 by 5 and get 20. And then the encrypted message would be 20. Well, the 20th letter. And then to undo that, I would multiply by the inverse of 20 mod 26, which of course should bring me back to position 4. If I do this all correct. So the idea here is we are going to again multiply by an inverse, right? But now we're going to use matrices for our key rather than individual numbers. So if our key is a matrix, then our inverse key is also going to be a matrix, right? And to that end, we'll have to do a matrix inversion. So we'll get to that in a second, but let's first do the encryption. So here I have a sentence. The ice cream was awesome. Now, the number of characters we have in that sentence is 21. You can just count it, right? The ice cream, that's 6. So the ice is 6, and then keep counting, you'll get 21 characters, right? So for this algorithm to work, you have to have an even number of characters in your sentence. So you can always just add a letter anywhere you want. For our purpose, we'll just stick it on to the end. So I'll just add a Q. Okay, so the ice cream was awesome, Q. Now that it's even, and again, you can literally put it anywhere, right? So if I had that, right? So THQE, right? I encrypt the message. Then when I decrypt it, I would obviously know that THQE is not a word, and I could remove the Q. Okay, so in any case, I have T gets assigned to the position 20, and H gets assigned to the position 8. Now, I'm going to pick a matrix to serve as my key, and I'm going to use 2, 3, 1, and 7. Okay? Now, in a little bit, I'm going to talk about what sort of keys are acceptable. It's going to turn out that the determinant of the matrix is going to have to be co-prime to 26. This will make sense in just a little bit. But the idea is we're going to take those positions here, 20 and 8, and we're going to multiply our key matrix. So this is our key matrix, right? And here's our message. Well, it's not our message, but it's the first part of our message. And we're just going to keep repeating this. So if I carry this calculation out, I get 6476. And this is very simple to show, right? So 2 times 20 is 40, plus 3 times 8 is 24. 40 plus 24 is 64. 20 plus 56 is 76. But we're going to have to do this mod 26. So everything is going to be mod 26, right? So this is going to become 1224. Great. I think it's a little dark. Okay, much better. So this would be our ciphertext. Okay, so once you carry the calculation out, you're basically gonna start off with TH, which is positions 20 and 8, and you're gonna end up with your ciphertext C1, C2, which is 12 and 24. Now, you just keep doing it to the rest of the sentence until you're done, and this will give you your secret message. What is 12? Let's see, A, B, C, D, E, F, G, H, I, J, K, L. So T would become L, and 24, that's X, Y, Z, so that's an X. So TH becomes LX. Okay, good. So that's not too difficult. Now, suppose instead that you did not know the plain message, right? So let's say that you and I are allies, and you only know two things. You know the key. So you know the key is 2, 3, 1, and 7, and you have an encrypted message. Okay, and let's say that the encrypted message was LX, and then a whole bunch of other stuff, right? So that's all you know. Well, L and X have positions 12 and 24, and if you do your work correctly, you should get back 20 and 8, which we know is T and H, right? So how do we do that? Well, if I have a matrix, AX equals B, and I know A and I know B, and I want to find X, the way I solve for X is I do that, right? The reason that makes sense is because if I multiply A inverse on each side, right, A inverse and A are going to cancel, and I'll have X equals A inverse B, right? So what is B in this case? Well, A is a 2 by 2 matrix, and B is our ciphertext vector. So that's literally 1224. Okay, so to summarize, if I give you a secret message, LX followed by a bunch of stuff, and you know the key, if you compute the inverse of the key and you apply this pair by pair to your secret message positions, you'll get the plain text positions back. So, right, so our secret message had LX followed by a bunch of stuff, and I said that this would give us, for C1 and C2, this is 12 and 24. Okay, so I'm just saying that L has position 12 and X has position 24. So that's what I've received, right? Or you could say that's what you received. I sent you a secret message. I sent you LX followed by a bunch of stuff, and you know the key. Okay, great. Well, you don't apply the key to this, you apply the inverse key. Okay? So what you literally want to calculate is 2, 3, 1, 7 inverse times 12, 24. Okay, so there's that glare. I can't do much about that right now. I guess I could not write on the glare. I'll try that. I guess the black pen works better. We'll do that. Okay, so okay, joking aside, I have the key, its inverse, and the position of the cipher message. If I carry this calculation out correctly, I should get P1 and P2, which are the positions of the plain message. Okay, so we need to find the inverse of that matrix. Okay, so remember that the inverse of a 2 by 2 matrix is 1 divided by the determinant. So 2 times 7 minus 1 times 3. And then I'm going to swap those positions and negate the off diagonals. Okay? Now, there's a catch, right? So let me simplify this a little further. Right, so here's the deal. We're working in mod 26. So we don't have negative numbers and we certainly don't have fractions. So what we need to do is we need to convert everything to mod 26. So when I say 1 divided by 11, I don't literally mean 1 divided by 11, unless I was working with ordinary matrices, right? So what I mean in this case is the inverse of 11 mod 26. So this is going to turn out to be 19. So let's rewrite that. This is 19, and I don't have negative numbers again, so, well, we'll get to that in a second, right? Okay, so I have this. Now, I'm going to go ahead and multiply 19 through everything, and if I do this calculation correctly, I should get 133, negative 57, negative 19, and 38. Okay, now remember, just like I don't have fractions, I do not have negative numbers, nor do I have numbers bigger than 25 when I'm working mod 26. So 133, this is going to equal 3, okay? 133 is 3, when you do the arithmetic mod 26. And negative 57, that's going to turn out to be 21 when you do the arithmetic mod 26. Likewise, negative 19 is 7 and 38 is 12. If this does not make sense, this step right here, this equal sign, if you cannot go from here to here, you need to review your basic modular arithmetic, okay? And if you have a question about that, we can discuss it tomorrow, but basically it's clocks, right? So clock arithmetic, right? So 26 and 26 is 52. And so, for example, if I had 50, this would be 2 less than 52. So that's 2 less than 0. So that would be 24, for example. Okay, so I have 3, 21, 7, and 12. That gives me the inverse of that matrix. Now, remember, at the very beginning, I said I had to multiply that by my cipher vector, okay? Okay, so I want to multiply this matrix by (12) and 24, right? So 12 and 24, that was the cipher message, L and X, right? L and X. So if I do this correctly, I should get the position vector back. Okay, so I just showed that this matrix right here, the inverse of 2, 3, 1, 7 is 3, 21, 7, 12. So I'm going to go ahead and rewrite that up here. So 3, 21, 7, 12, and then I'm going to rewrite this. Okay, so 12 and 24. And if you do this ordinary step correctly, your number should come out to be 540, which is nothing more than, okay, this is just going back to basic matrix multiplication. It's 3 times 12 plus 21 times 24. That's 540. So 3 times 12 plus 21 times 24 is 540. And then 7 times 12 plus 12 times 24, this is 372. And of course, we don't like those numbers because they don't exist mod 26. So we're going to convert this to 20 and 8, and that can be shown, right? You just keep subtracting multiples of 26 until you cut it down to a number that you can handle, and you'll see that it should give us 20. And of course, this is the cipher position for C1 and C2. And if you just go through your alphabet, right, the 20th character of the English alphabet is T, and the 8th one is H, right? So the original message, if you recall, was the ice cream was awesome, I believe, or the ice cream is very awesome, or the ice cream is awesome, something like that. Well, it starts off with the word the, and so we got TH, and this concludes Hill's system, and that is all I want you to know for today. If you can do this, you're fine. You're golden.